This page breaks down a really core concept for ARM processors, the fact that they can use two different types of instruction sets. Think of it as having two ways of communicating, one using full, detailed sentences, and another using shorter, abbreviated messages. The first type, used by early ARM processors, is the standard ARM instruction set. This is the full sentence version. Every single instruction is 32 bits long. This provides a lot of power and delivers very good performance. But it has a couple of drawbacks. Using 32 bits for every instruction means your program code takes up more memory compared to older 8-bit or 16-bit processors. And logically, processing these larger instructions consumes more power. To address these issues, ARM developed the thumb instruction set, specifically thumb-I, which stands for the first version. This is our abbreviated message version. It's a 16-bit instruction set that was first introduced with the ARMv7-TDMI processor way back in 1995. Now, an important detail is that thumb is a subset of the ARM instructions. It doesn't introduce brand new operations. Instead, it provides 16-bit versions of the most frequently used 32-bit ARM instructions. The main advantage here is something called code density. Because the instructions are half the size, the overall size of your compiled program can be reduced by about 30%. This is fantastic for devices with limited memory. Of course, there's a trade-off. This compression comes at a small cost to performance, which is reduced by about 20%. So, how does the processor handle two different instruction sets? The most brilliant part is that it can use them together, even within the same program. The diagram at the bottom explains this process visually. You see incoming instructions, which can be either a 32-bit ARM instruction or a 16-bit thumb instruction. If it's a thumb instruction, it first has to be expanded back to its 32-bit equivalent. That's the job of the thumb remap to ARM block. The core of the processor is designed to decode 32-bit ARM instructions, so the 16-bit thumb instruction is just a compact encoding. After the remapping, a multiplexer, which is essentially a digital switch, selects which instruction to send to the ARM instruction decoder. This switch is controlled by the T-bit in a special processor register. When the T-bit is 0, the processor is in ARM state and it selects the 32-bit instruction directly. When the T-bit is 1, the processor is in thumb state and it selects the output from the thumb remap block. Ultimately, the ARM instruction decoder only ever sees a 32-bit instruction, but this mechanism gives programmers the flexibility to mix and match. They can use the high-performance ARM instruction set for critical routines and the space-saving thumb instruction set for other parts of the code to keep the application size small. On the next page, we'll see how this concept was evolved even further. Building on what we know about the original thumb instruction set, let's now look at its evolution, the thumb-2 instruction set. Think of thumb-2 as the best of both worlds. It's not limited to just 16-bit instructions. Instead, it's a variable-length instruction set that cleverly combines both 16-bit and 32-bit instructions. Why is this combination so powerful? As we see here, when you compare it to using only the standard 32-bit ARM instruction set, you get a significant code size reduction, about 26%. This means your programs are smaller, which is great for memory-constrained devices. But the really brilliant part is that you achieve this without the major performance hit of the original thumb. It maintains a performance level very similar to the full ARM instruction set. So, with thumb-2, you get the code density benefit of thumb and the performance of ARM. It was a major step forward. Next, we have something called the Thumb Execution Environment, or thumb-E. This is a specialized version of the instruction set designed for a very specific purpose, running dynamically generated code. What does that mean? Think about environments like Java or .NET. Often in these systems, the code isn't fully compiled before you run it. Instead, a process called just-in-time (JIT) compilation happens, where code is compiled on the device itself, either right before or during execution. ARMv7-A includes features that make it an excellent target for these JIT compilers, allowing them to produce efficient machine code on the fly. It's all about making modern, managed code applications run better on ARM processors. Finally, how do these pieces fit into the bigger picture? The last point tells us exactly that. The ARMv7-A architecture, which is the foundation for the high-performance Cortex-A series processors we'll be studying, is based on ARMv7-A and ARMv7-A. This integration means that modern application processors are inherently designed to be both highly efficient with their memory usage, thanks to ARMv7-A, and optimized for running complex software environments that use dynamic compilation, thanks to ARMv7-A. This sets the stage for the powerful and efficient devices we use every day. At the heart of the ARM processor is its set of registers. Think of these as the CPU's immediate, super fast workspace. On this page, we see how they are organized. The processor has 16 general-purpose registers that are visible to the programmer at any given time, named R0 through R15. However, as you can see, they aren't all used for the same things. Let's first look at the main group, from R0 to R12. These are the true general-purpose registers. You can use them for almost any data manipulation. When you're adding numbers, storing temporary values, or moving data around, you'll primarily be using these registers. They are your main workhorses. Now, things get more interesting with the last three registers, R13, R14, and R15. While you can sometimes use them for general data, they each have a very important, special role assigned by convention, and in some cases, by the hardware itself. Let's start with R15, the program counter, or PC. This is perhaps the most critical register. It doesn't hold data from your program. Instead, it holds the memory address of the next instruction to be executed. As the processor runs, it fetches the instruction pointed to by the PC, and then it automatically increments the PC to point to the next instruction in line. It's what drives the program forward, one instruction at a time. Next is R14, the link register, or LR. This register is essential for calling functions or subroutines. When you make a function call, the processor needs to know where to return to when the function is finished. The link register is where this return address is automatically stored. It's like leaving a bookmark in a book when you go to look something up in the index. Then we have R13, the stack pointer, or SP. The stack is a region of memory used for temporarily storing data, like local variables in a function or saving register values. The stack pointer's job is to always point to the top of the stack. As you add data, push onto the stack, or remove data, pop from the stack pointer is adjusted accordingly. It's crucial for managing function calls and memory. Finally, at the bottom, we have the program's status registers. These aren't for general data at all. They hold information about the state of the processor. The first is the CPSR, or Current Program Status Register. This register contains important flags. For example, after an arithmetic operation, it will tell you if the result was 0, negative, or if a carry occurred. It also contains control bits that determine the processor's current operating mode and whether interrupts are enabled or disabled. It's the processor's main status and control panel. The second one is the SPSR, or Saved Program Status Register. This one is very clever. It's a backup for the CPSR. When an exception occurs, like an interrupt from a peripheral, the processor has to stop what it's doing to handle the exception. Before it does, it automatically saves the current state of the CPSR by copying it into the SPSR for that exception mode. Once the exception is handled, it restores the CPSR from the SPSR, allowing the program to resume exactly where it left off. This is why the slide notes it's only present in exception modes. You only need this backup when an exception happens.